Today we're going to begin a very important topic in organic chemistry that is very extensive. It's going to cover chapters 16 and 17 from our textbook of Wade, and it's going to be the topic of benzene chemistry. Benzene chemistry covers these two chapters, and there's just a lot of material here, so it's going to take a little while to get through this, but what we'll do is begin with some of the introductory stuff about benzene and then get into the chemistry of it later. This is a very important topic because a lot of exams, such as the MCAT exam, covers a lot of benzene chemistry, and other types of exams use it a lot as well. So let's go ahead and begin by drawing the molecule of benzene. As you can see, benzene is a 6-membered ring with 3 conjugated double bonds. One of the things to realize about benzene is that each carbon of the ring has 1 hydrogen. Okay, so benzene is a very unsaturated molecule here. And one of the things about benzene is that we can draw a resonance structure with it. One of the rules that we did not mention earlier with resonance is that we can move pi electrons toward a pi bond. We can move, in a sense, pi bonds toward pi bonds as long as they are conjugated with each other. So here we have 3 conjugated pi bonds, so we can move them toward each other like that. And get a resonance structure like that. So you can see that the 2 resonance structures just are basically the same, except just these movements of pi electrons within the ring. One of the things that we also didn't cover when we did resonance theory is look at something called the resonance hybrid. The resonance hybrid, this is the true structure of the molecule. Because as we've been covering resonance theory, recall that we have more than one resonance structure. And so you might ask the question, well, which structure do we use? Which is the real structure? Well, the real structure is what's called the resonance hybrid, where it's a hybrid, or it's a mixture of these resonance structures. So for benzene, if we were to draw its resonance hybrid, we might draw something like this, where the pi electrons are what? Evenly distributed throughout the whole ring. See that? Because of the resonance, they are equally distributed around the ring. And so we can use this dotted line to show that. Or what we most often do with benzene is just simply draw the ring with a circle in it, or a donut. This is the most often way that we'll draw benzene. we'll draw it like this, but we'll also draw it like this to show that resonance hybrid, showing the pi electrons are smeared around the ring. If you had molecular vision, were able to look at the electrons, you would see a smearing of electrons, a huge electron cloud like a donut that is hovering above and below the ring. And so we'll draw it with this donut here. Now, one extra piece of information with benzene, since it has this extended conjugation around the ring and its resonance hybrid can show that distribution of electrons around the ring, we say that it has resonance energy stabilization. Okay? Resonance energy stabilization. That if a molecule has this nice distribution of electrons around it, benzene, and we'll see with others, have this high resonance energy stabilization. And if something has high resonance energy stabilization, we say that the molecule is aromatic. Okay? So benzene is our first example of what is an aromatic molecule. Okay? And that's what we want to move into now, is what are the rules, or how can we predict whether a molecule is aromatic? Because benzene is not the only molecule out there that's aromatic, that has this high resonance energy stabilization. There are others. So let's go ahead and look at the rules for something being aromatic. Okay, we're going to cover three different labels that we can give molecules. The first one's what's called aromatic, so we'll call these the aromatic rules. The second one's what's called anti-aromatic. We'll look at those rules later. And then third is something called non-aromatic, and we'll look at those rules in a little bit. But first of all, what are the rules for something to be aromatic? Okay, there's two rules. The first rule is that we must have a cyclic molecule of conjugated electrons. Okay? We saw benzene fit that category very nicely. Okay? But the second rule is even more important. Is that this cyclic ring must have one of these numbers of conjugated electrons. Let me write them down for you. Okay. It's a series of different numbers where we could have anywhere from 2 to 6 or 10 or 14 and so on. Okay? These are what we call the magic numbers for aromaticity. Okay? As you look at these numbers, you might ask which one of these numbers fit for benzene. Okay, so here was benzene. How many electrons were conjugated in that ring? Do you count them? There are what? 6. And 6 indeed is one of the magic numbers. You say, where are you getting 6 from? I only see 3. Well, yeah, you see 3 double bonds, but remember that there's 2 electrons in each. So we have a total of 2, 4, 6 electrons that are in that conjugated system. Okay? Now, these magic numbers, you can just simply memorize them. You just keep adding 4, so the next one would be 18, and then 22, and so on. But there's also a formula to remember these numbers. And it's called the 4n plus 2 rule. Okay, so how does this 4n plus 2 rule work? Well, n is simply an integer that can start with 0 and then keep going up. Okay, so n, write it down, has nothing to do with the molecule. And it has nothing to do with the molecule, it's just simply integers to help us remember what these magic numbers are. Okay? So that if I then look at what 4n plus 2 is, if n is 0, this would equal 2, because 0 times 4 plus 2. If n is 1, you get 4 plus 2, or 6. If n is 2, you get 8 plus 2, which is 10, 3, 12 plus 2, 14, and so on. Okay? So this is just a formula to help you remember these numbers. Okay? But mark it down. Students mess it up all the time. N has nothing to do with the molecule. Okay? So just get that out of your head right off here. Okay? And these magic numbers, using the 4n plus 2, is what's called Huckel's rule. Huckel's rule. So Huckel's rule follows a molecule that's cyclic with conjugated electrons having one of these magic numbers that follows the 4n plus 2. Okay? All right, so those are our aromatic rules, okay? Now, let's go ahead and go on to what makes something anti-aromatic. Anti-aromatic rules. You might ask, well, what does it mean if something is anti-aromatic? Well, it simply means that the molecule is extra unstable. Okay? So remember, if something is aromatic, it means that it has high resonance energy stabilization. That molecule is very, very stable. Okay? Aromatic used to have the definition of just simply how does it smell, okay? And we use that as well, but in chemistry we're using it toward stabilization. So if something is anti, it's total opposite, so it's extra unstable. So what are the rules for something to be anti-aromatic? Okay, so the first rule is the same as the aromatic rule. That is, you must have what? A cyclic molecule with conjugated electrons in it. And that conjugation has to go around the whole ring. Okay? So the first rule doesn't change. It's the second rule that changes. In that we must have a different number of conjugated electrons around the ring. So these numbers change, and they change to these numbers here: 4, 8, 12, and so on. Okay? So we just keep adding 4 to these. Okay? So we must have these numbers of conjugated electrons around the whole ring. Okay? And this rule follows the 4n rule, okay, where n starts with 1, 2, 3, and so on, okay? So that if n is 1, 4n is 4, 8, 12, and so on. The next one would be 16, and so on. So anti-aromatic follows the 4n rule. Aromatic follows the 4n plus 2 rule. Okay? So again, you can either just memorize these magic numbers or just use the 4n rule. And again, this has nothing to do with the molecule. N are just integers to help you remember these magic numbers. Okay, let's go on and look at our last rule. The last rule deals with if a molecule is non-aromatic, if it's non-aromatic. Okay? So what would it mean if something is non-aromatic? If something is non-aromatic, it's in between the stability of aromatic and anti. Okay? So if you were to look at the stabilities here, aromatic is much more stable than non, which is much more stable than anti. Okay? So there's our stability series. So how do I know if something is non-aromatic? Okay? Well, these are when we have conjugated electrons that don't go around the whole ring. Okay? And there's no magic numbers for these. It's just simply when we don't have a continuous series of electrons conjugated around the whole ring. Okay? So what we want to do now is look at some examples of these three things: anti, aromatic, and non-aromatic. Okay? So let's look at some examples of these. Let's start off with this molecule here. Can you predict whether that molecule is aromatic or whatever? Well, what do we have? We have a ring, good. We have conjugated electrons around the whole ring, good. So that means it's either anti or aromatic. Then how many do we have? We have 4. And 4 is a magic number for what? Anti. Okay, so this molecule would be extra unstable, wouldn't it? Okay. Let's look at another example. Okay. Here is the molecule pyridine that we will study later on in the course. Okay, so pyridine has 3 conjugated electrons, pi bonds, and we have this lone pair on the nitrogen. What will this one be? What do you think? This one turns out to be aromatic. So this one is extra stable. Okay, let's figure out why this is aromatic. Okay, we have 2, 4, 6 conjugated pi electrons. And so it fits that magic number. Now some of you might say, well, what about this lone pair on the nitrogen? Wouldn't that count as 8 and so make it anti-aromatic? Answer is no. Okay? This lone pair is not used by the molecule for continuous conjugation. You see, the molecule is saying, okay, I have 3 sets of conjugated pi electrons, and I'm just going to use those because that gives me aromaticity, extra stability. So this lone pair remains outside the ring. It's not used. And this lone pair, since it's not used, is going to be basic. So pyridine is a very basic molecule. In fact, we would classify it as an aromatic base. Okay? Let's look at another example. Okay. Here is the molecule furan. And what do we have with furan? We have 2 double bonds that are conjugated. Then we got these electrons on the oxygen. What do you think this is going to be? Well, this molecule is going to be aromatic. Say, how is this one aromatic? Well, if you look, what the molecule does is it uses these 2 pi electrons, so that's 2, 4, and then it's only going to use one of these lone pair, either this one or this one. And it says, as long as I can use one of those, I'm going to get stability, and so I get that aromatic setup, okay? So here, we would say these are used. Not used. So our magic number fits here at 6. So with furan, we can often redraw it something like this, where again, we use a circle to designate aromaticity of the ring. We could also have done that with pyridine. Put a circle inside of its ring. Okay, so both furan and pyridine are both aromatic. Okay, so something to build on here. So let's look at some more examples. about this molecule here? Okay. Here we have lone pair on both oxygens and double bonds right here. Well, do we have a continuous series of conjugated electrons? Yes. Here, 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 and here. And we have a total of what? 2, 4, 6, 8 to get that continuous series. And so what magic number does 8 fall under? It falls under the anti-aromatic system. Okay? So again, I'm only using one set of the lone pair to get a continuous series around the molecule. After I do that, I then ask, what are my total number of electrons? And this one is 8. Okay? So this lone pair is used, and this lone pair here is used. Okay? All right, let's continue with some more examples so that we're not caught off guard by things on an exam. Okay. What about this molecule here? Okay. Here we got 2 double bonds. They are conjugated, aren't they? Here. Okay. But can I get around here? Okay. I can't, can I? I can't get my resonance this way. I can only get it this way, so I'm stuck down here. So what category of molecule would this be? This would be non-aromatic. Okay? Because I can't get my electrons delocalized through this carbon here. Okay? What could I do to make that molecule aromatic or anti-aromatic? Well, let's suppose I had a lone pair on that carbon. Okay? So now I have conjugation here, and I have conjugation around this carbon, don't I? Remember, lone pair next to a pi bond, I can push. And so now I have a continuous series. So now my first rule is met. Okay? And what would be my magic number? 2, 4, and 6. So this here would be aromatic. Okay? So this molecule is an anion. Okay? That's aromatic. Sometimes, again, we can redraw it with the circle in there to show it's aromatic. It's aromatic because it has the lone pair on that carbon, and it has a negative charge there, just kind of curving the negative charge. It's a very happy molecule, isn't it? Because it's aromatic. Okay? So we can be a little cute with this cyclopentadienyl anion. Okay? Well, how could I make the molecule anti-aromatic? Well, let's suppose instead of having a lone pair on that carbon, I put a positive charge. Is my first rule met, letter A? Yes, it is. Because now I have allylic, don't I? So now I have conjugation or resonance through this side as well as this side. Okay? So now I then go under rule B and ask, what's the magic number? The magic number here is what? 2, 4. So this would be anti-aromatic. Okay. So our setup here, no resonance this way, resonance, resonance. Here we have a total of 6. Here we have a total of 4. So this carbocation on this ring would be a very what? Unstable carbocation. Okay? So this is our number of examples, and there's many more examples in your homework that you should look at. Let's look at a few more. As this is just such a very important topic. Okay, let's look at this molecule here. Okay, this molecule here is called purine. Okay. And we want to figure out, is this molecule aromatic or not? Okay. Well, with this one here, what's our continuous setup? Well, here, this aromatic ring, 2, 4, 6, so that's good, but let's continue into this ring here. This is conjugated with this lone pair, conjugated with this double bond, which is conjugated with this double bond. So what's our total? 2, 4, 6, 8, 10. Was 10 a magic number for aromatic? Yes, it was. Okay. So that is an aromatic molecule. Okay. So what else can we say about purine? We can say that this lone pair on this nitrogen is not basic, right? Because it's used for aromaticity. Okay? So if a lone pair is used for aromaticity, that is not available to be a base. But all the 3 other nitrogens their lone pair are not used, are they? And so these other 3 nitrogens would be basic nitrogens because those are available to attack an acid. Okay. Let's look at something else here. Let's look at this molecule. Here we have nitrogen with a positive and these 2 double bonds inside. let's remove one of these hydrogens off the nitrogen. If I do, those will go back in and form a lone pair. And so we would end up with this. If we end up with this, let's ask ourselves the question, is this aromatic? Yes, that would be aromatic, wouldn't it? Because we have what? 2, 4, 6 in the continuous ring. Okay? So that molecule is aromatic. So let's ask ourselves the question then, would this molecule really like to lose one of those hydrogens? Yes, it would, wouldn't it? Because by doing so, I get aromaticity as the result. So I would what? Get a conjugated aromatic base. And if this hydrogen wants to be lost, it wants to be given away so that it can form that conjugated aromatic base, which is what? Very, very stable. So it wants to give this away what? Badly. If a hydrogen wants to be given away badly, what do we say that that hydrogen is? We say that that hydrogen is thus very acidic. Okay? So here we just learned something, that if we have a molecule that has a hydrogen on it, that if it can be lost to form a conjugate base that is aromatic and so very stable, that that hydrogen is going to be very acidic. And just to give you an idea, its pKa is 0.4. Okay, so it's a very small, very low pKa. So that is a very acidic hydrogen. Okay? So any kind of base can come along and take that very easily, so that I get this very stable conjugate base as a result. Okay? So this is one way we can use this, is to predict acidic hydrogens that are in our molecule. Okay, so with this under our belt, I think we'll stop here for today.